Hey there. Hey there, AP Stats kids. Hopefully the sound's working today. I'm using my laptop mic, so it might not be as good. Today we're looking at 9.2a, probably. We're going to look at tests about a population proportion. We're going to learn how to check our conditions, calculate and find our p-value, and perform significance tests. So let's get right to it. Alright. So the conditions for a significance test are going to look very similar to when we made a confidence interval, right? We're looking at random, 10%, and large counts for proportion, right? All these are the same. The only difference is we're using null p, which is from, so you're using the value from your null hypothesis. So think about this as coming from your null hypothesis, right? Okay, so you're going from your estimate. Alright? So, but these should all look very similar. The only thing that changes is where P comes from. Before P was the statistic from our sample. Now we're looking at P is our null hypothesis. Alright. Not too bad. Oh, and here it says that again, right here. You guys can read. Both have to work for it to be normal, right? If it's not normal, we can't use critical values. Well, actually, that you'll see. You'll see. All right, let's do an example where we check conditions, see if we can do a significance test about a proportion, not a mean. All right. So according to the U.S. Census Bureau, the proportion of students in high schools who have a part-time job is 0.25. Local high school thinks that it's less than the national figure, so she wants to carry out the test at 5% significance, so being 95% confidence, so alpha is 0.05. Your null hypothesis is that P equals 2.5, and your alternative is what you think is true, and you think it's less than 2.5. So, she takes a random sample of 200 kids from the high school, and 39 have a part-time job. Let's check the conditions. Alright, so first thing we gotta check, is it random? Yeah, it is. There's a random sample of 200 kids. We did. 10%. 200 kids is less than 10% of kids at a large high school. If you go to my high school, that's every kid in high school. So that would have failed. But at large high school, you probably have 1,600 kids. Well, actually, that would still fail. This must be a huge high school of like 2,000 kids. Holy smokes. That passes. Large counts. Again, we are using our values from our null hypothesis, right? So we're using the 0.25 from our null hypothesis times our sample. We got 50 and 150, which are both bigger than 10. So this is normal. I'm going through this really quick because we've done this all before, guys. We've done this all before. Where should I put my face? There's my face. Alright, we good? Why do they call it a cursor? Does it swear a lot? Alright, a basketball player claims to make 8% of their free throws. You think they're exaggerating. That's wrong. So that means your null hypothesis is going to be 0.8, but you believe P is less than 0.8, right? So let's actually perform this test, y'all. Let's do this. Let's see if I took any noties. Yeah, I did. I said that's wrong. I'm absolutely going to pause this right now to make sure that there's sound. Hey guys, I'm back. I checked sound and went to record the rest, and it didn't record, and I upload it, and then I have to remake it again just like I did the last video. So this chapter 9 has been so much extra. So last time, it feels like a day ago, but for you it was a second ago. There's a basketball player. We think they are not an 80% free throw shooter. We think it's less than 80%. So here we go. Wait, we might have done this one too. Well, I did. I don't know why I did or not. So if we assume the null, if we assume that they're an 80% free throw shooter, let's talk about what the shape of that distribution is going to look like. Well, it's going to be approximately normal because 0.8 times 50 is
bigger than 10, and 0.2 times 50 is 10. So we're good. Large counts. The center should be at 0.8, right? And the variabilities are standard deviation. Now we're using our formula that we've used before, which is square root of p times 1 minus p over n. But now we're doing p naught, which is our null hypothesis p. So we're using 0.8. 0.8 times 1 minus 0.8 over 50. Square root is 0.056. Oh, making videos over and over again is great. I feel like I just did this. I'm probably talking super fast. All right, here we go. Let's go on to the next slide. Everybody, okay. That's what it looks like. So we have 0.8 in the middle, 1 standard deviation on both sides. But remember the sample from 9-1. They only made 32 of 50. So if you were to shade that region, that's very rare to happen if the null is true. Okay. In fact, we're going to, oh my gosh, I have to do this again. Let's find out the z-score of that proportion. So remember z-score? It's kind of like what you got minus mean over standard deviation. Remember, it was standard deviation. We're doing the same thing. Your statistic minus your assumed mean over standard deviation. So that was 2.83 standard deviations below the assumed proportion. Oh my gosh, there's another one coming. Oh, I need to pause this. It's a catastrophe. I'm allergic to learning. All right. So that, remember we use z-scores to compare stuff. If you know how many standard deviations away, you understand how much better or below it is. It's a way we can compare everything. You standardize it. That's standardized tests are standardized. They're based on your rank to everyone else who took that test. So that's your standardized test statistic. That's your Z. Get used to finding it. You have to find it every time you do one of these problems. Even if you do a calculator. Here's the formula for it. Statistic minus parameter over standard deviation is just z-score. We've done this before. Now, we can convert the standardized statistic into a p-value, so probability value of getting that if the null is true. So if we have our z-score, negative 2.83, use table A in your book, and you look at it, and you go to 2.8, 0.03, and you'll find that magic number. Or you can do inverse norm, not inverse norm, normal CDF. Yeah, normal CDF. Another way you could have done it, which is actually the way I prefer, but you need to find your z-score anyways. You could have done normal CDF. What's the chance of them being a negative 99999? 0.64, right? Because I shot 64%, 64% or lower. The mean is 0.8, and the standard deviation is 0.0533, and that's based on that formula, right? Okay, and that should also give you 0.0023. I usually do it the normal CDF way. Understand what a test statistic is, though. All right, that's your p-value. That's your probability of shooting that or less if the mean is 0.8. Not the mean, but the parameter is 0.8. I'm sorry. Please forgive me. I'm this guy at the cash register. I made this joke already. Second time in this video. Same problem as before. School administrator thinks less than 25% of their students have a job. We're going to do this test at alpha being 0.05, so 95% confidence. He selects 200 people, 39 have a part-time job. we already know the conditions are met for this. So let's find our p-value and such. So right away, why is the 39 out of the 200 give us some evidence for the alternative hypothesis that's less than 0.25? Well, because that proportion is 0.195, and that's less than 0.25. So right away, that's a red flag, like maybe it is lower. All right, maybe the alternative is correct. B, calculate the test statistic. All right, we're going to do this. So again, we're taking what we got in our sample, our statistic. We're subtracting our parameter, or our null parameter. And we're dividing it by our standard deviation. I'm rewriting what's right next door. I got negative 1.8. So our test statistic is 1.8 standard deviations below the null. Okay. Now we take that negative 1.8, and if we use table A, we get 0.0359. We'll go over that more in class. Or you could have used your calculator, done normal CDF. You're doing that and below, so negative 999. Your test statistic, what you actually got, what the assumed parameter is, 0.25, and then your standard deviation over here. Okay, and that will also give you about 0.036. All right? Both ways work. Oh, those are negative signs, not twos. Those are supposed to be negative signs. All right, now to interpret the most important part. Our p-value is 0.0359, which is less than 0.05. Because it's less than it, it means the probability of getting that number by chance, if the null is true, is very low. So the null is probably not true. So we're going to reject the null. We have convinced, and that's convincing evidence when you reject it. We have convincing evidence that the proportion of students is less than 0.25. We accept the alternative hypothesis. Okay? We don't accept it, but we say there's convincing evidence that it is true. Okay. This is a four-step process. You can recognize these four steps. State, plan, do, conclude. The only difference between this and confidence interval is when you get to that do. When you do the do, Mountain Dew, by the way, Mountain Dew, my opinion, disgusting. It's disgusting. But this time we're going to look for our sample statistics. We're going to find the standard statistic, our z-score. And then we're going to find the p-value, probability value. And we're going to use that p-value to draw a conclusion. All right? Now, what do the three conditions that have to be met have to do with this equation? The random condition coincides with the top part. If we're random, it means the sample we took is a good statistic. If it's random, it means that the statistic we took correlates to everybody, right? So that's why random condition lets us take a sample and say that it works. Large counts lets us say it's normal, so it means our z-score, we can do a standardized test statistic. If large counts doesn't work, then z will not find us our p-value. Okay? Critical values only work if it's normal. 10% lets us find the standard deviation, the variability, without replacement. Because remember, if you have replacement, it doesn't matter, but in real life, you're not going to see that occur. Now, if you're doing a one sample test, or these are going to be one sample z-tests, because we are taking one sample and drawing conclusions based on our one sample. And it's a z-test for proportion, not for interval anymore. All right. If your alternative is you think it's bigger than your null, you're shading the top. You're gonna have to subtract to find your p-value. We'll talk about that in class. If it's less than, it's easy. You just plug it in. You're gonna get your stuff. And if it's not equal to, you have to find both tails. So you have to multiply by 2. We'll see that. Holy sack of potatoes. Alright. So there's a shipment of potatoes. We're looking at quality control standards. And they want to know if there's convincing evidence that 8% have blemishes. And they'll be sent why otherwise. Otherwise, they'll make potato chips. They took a sample of 500 potatoes, 47 had blemishes. Is there convincing amount that there's more than 8% and have blemishes? Alright, let's do it. State, plan, do, conclude. State, plan, do, conclude. So first we're going to state. The null hypothesis is always what's given to us, right? So for this one, it's 0.8%. We are testing if there's more than 8%, because if there is, we send them back. P is the true proportion of potatoes in the shipment with blemishes. And we're going to use alpha, it's 10%, so 9% confidence. Plan. It's going to be a one sample test for P. Okay? What that means is we're going to find our Z. We're testing for a proportion, right? So, is it random? Hold on. All right, there we go. There's a ball under. Random. Yes, we took a random sample of 500 potatoes, so we know our statistic will be good. 10%. Is 500 less than 10% of all potatoes in shipment? More than likely. Large counts. Is it normal? Will Z help us? Yeah. We get 40 and 460, so we good. Do. Do the do. 2 ways to do this. Get out of here, face. Alright. So first you find your statistic, right? You do 47 divided by 500, because that's the proportion of potatoes in your sample that had blemishes. Next, you use this for your z-score. So you do your statistic minus your p-naught, right, over your standard deviation. And for your standard deviation, you're using your null hypothesis, right? You get 1.15. Once you find that, you use your table, but now in your table, that's finding this part. Or I'm sorry. Whoopsie. It's finding this part. But what you care about is this part. So you have to do 1 minus your table to get your p-value. Okay? Because this is a right tail test, not a left tail test. Or you could have went to your calculator and you could have done normal CDF 0.094 because it's above to 99999. Standard deviation is our null. Not our standard deviation, our parameter. This is our standard deviation. 0.08, 0.92 over 500. Okay? Any way you do it, we get our p-value of 0.1251. So, let's make a conclusion. So because 0.1251 is greater than our alpha of 0.1, we fail to reject the null. There is not convincing evidence that the true proportion is greater than 0.08. There's only convincing evidence if our p-value is less than alpha. Okay? Pause this, write it, love it. Good? Good. All right, let's keep trucking. Read this. Love it. Learn it. If we fail to reject, we don't have convincing evidence for the alternative, right? So it sounds like you believe the null, but that's not true. You just say there's convincing. Oh, and also please write this out. Don't use shortcuts, guys. I'm getting real sweepy. More stuff. If you do your calculator like I do for normal CDF, please still state your Z and your p-value, or else they will not give you full credit for the do step if they don't see a Z score, a standardized test statistic. Please find that. You're subtracting and dividing. All right. Two-sided test. So far, we've only dealt with right tail, left tail test. Okay. Now, what do we do if it's a two-tail test and we're saying that we don't believe the alternative is it just doesn't equal the null? So it can be either direction. I'll tell you. It's easy. You're just going to multiply by 2. Okay, hold on. So 68% of high schoolers have never smoked a cigarette. And this guy wonders if that's true. So he takes a sample of 150 students. 90 say they've never smoked a cigarette. Is there convincing evidence that CDC's claim does not hold true at their school? Jan Hoen's school. All right. So what do we want to test? State. The null is what the CDC said, right? Jan didn't say it's above or below. They just said it's not equal to. So we aren't saying greater than or less than. We're saying not equal to. Our P is the true proportion of students who have not smoked a cigarette. We did not say what our alpha is, so we're going to assume 0.05. Plan. Everything checks out. I'm going through this quick. I just want to get to where it's different. Stop and read this if you need extra help. Do. So first we find our statistic, right? 90 or 150 was from our sample. And we're going to use that number minus our null all over our standard deviation of null. I don't know if that's correct. We get negative 2.1 standard deviations away from the mean below. Now, nothing new. Now, we use our table, and we get a p-value of 0.0179. That's only for this tail. So all you do is you times it by 2 to get both tails. So your final p-value is that. Even if you're doing this in normal CDF way, it's very similar. You do normal CDF. They got below, so I do negative 99999 to 0.6 to 0.68 and whatever the standard deviation is, right? And then I take this result and I times it by 2 because that gave me the left tail. If we times it by 2, it'll give me the right tail. All right? So on a two-tail test, you just multiply it by 2. That's a negative. So because our p-value is less than our alpha, we reject the null. We have convincing evidence that the proportion of students at school who have never smoked a cigarette differs from the CDC's claim. Long video. I'm sorry. Enjoy. Oh, read this first. I'll talk about this in class. Now enjoy.